Okay, so let's work to solve example 3.6 from the OpenStax textbook together. Let's first read the problem. A particle is in motion and is accelerating. The functional form of the velocity is v as a function of t is equal to 20t minus 5t squared meters per second. In part A, they want us to find the functional form of the acceleration. In part B, they want us to find the velocity at 4 different times. In part C, they want us to find the acceleration at 4 different times. And in part D, they want us to interpret the results in terms of the direction of the acceleration and velocity vectors. So okay, what is our known? Our major known is the equation they give us in the problem. We know at exactly every moment in time how fast this object is moving, right? Because we know the equation for its velocity as a function of time. I'm going to do the same thing I've done in the past and rewrite this a little bit to make it more clear what these constants are. So the velocity as a function of time is equal to 20. That 20 must have units of meters per second squared, so that when I multiply it by time, I get units of meters per second, which matches our velocity. And then minus 5, the units of that must be meters per second cubed, right? So that when I multiply it by time squared, I get the time squared canceling 2 of those seconds and giving me something of meters per second. All right, so I think the units, when I write it in this way, make a little bit more sense. Okay, so for part A, we need to find the functional form of the acceleration. Well, we need to bring in our conceptual knowledge here about what is acceleration. Acceleration is a change in velocity, and in fact, instantaneous acceleration is the derivative of velocity as a function of time. So since I know a functional form of my velocity as a function of time, I can just take the derivative of that, and I can find my acceleration. Okay, so taking the derivative of this velocity formula, the t just goes away. I get 20 meters per second squared minus 5 meters per second cubed times the t squared just becomes 2t. Alright, so there I have an equation now for my acceleration as a function of time. Okay, 20 meters per second squared minus 10 meters per second cubed times time. And maybe I'll write it out for you like that. So okay, we now know an equation for the acceleration and the velocity. So in part B, they want us to find the velocity at 4 different moments in time. In part C, they want us to find the acceleration at 4 different moments in time. So let's actually do part B and part C together and make a nice little table. All right, so I'm going to, at these 4 different times, let's solve at time equals 1 second, time equals 2 seconds, time equals 3 seconds, and time equals 5 seconds. Let's try to find the velocity and the acceleration at those moments. So let's first try to solve the velocity at time equals 1 second. Well, again, I have an equation for the velocity at every moment in time. So to find the velocity, I just have to plug in my 1 second. So I have, and I'll just drop the units here just to make this table a little bit more readable. I have 20 times 1 second minus 5 times 1 second squared. So 20 minus 5 is equal to 15 meters per second. Okay. At time equals 2 seconds, I have 20 times 2 minus 5 times 2 squared. All right, so I have 40 minus 20. All right, so I have a velocity at that moment of 20 meters per second. At time equals 3 seconds, I now have 20 times 3 minus 5 times 3 squared. All right, so when I plug that in, I get 60 minus 45, or 15 meters per second. So we're back to our original velocity. And at time equals 5 seconds, I have 20 times 5 minus 5 times 5 squared. And so I have here 100 minus 125, and so that gives me negative 25 meters per second. So at that point, my velocity has gone negative. Okay. So let's do the acceleration now. So that was basically the answer to part B. Let's do the acceleration now. So the acceleration, I have a formula for acceleration as a function of time. So let's use that. I can plug in time equals 1 second. That gives me 20 meters per second squared minus 10 times 1. So that gives me 10 meters per second squared. At time equals 2, I have 20 minus 10 times 2, so 20 minus 20 is 0 meters per second squared. At time equals 3, I have 20 minus 10 times 3, so that gives me negative 10 meters per second squared. And at time equals 5, I have 20 minus 10 times 5, so that gives me 20 minus 50, or negative 30 meters per second squared. Okay, so we've now finished part B and part C, and now we can do part D, which is just basically trying to understand what this means. Okay, so maybe I'll just add another column to this table, and this will be where I'll write down my interpretation. So at time equals 1 second, right, at this moment in time, we have positive velocity and positive acceleration. Right, so our acceleration vector is in the plus x direction, and our acceleration vector is also in our plus x direction. So our change in velocity is in the plus x direction. So we're getting faster, right? We're definitely speeding up. Right, so in this moment, we're speeding up. Okay. At time equals 2 seconds, our velocity is 20, but our acceleration is 0. So at that moment in time, for an instant, we're just going at a constant speed. We're not speeding up or slowing down, right? So we have a constant speed for that moment. At time equals 3 seconds, we have positive velocity but negative acceleration. So our acceleration vector is opposite our velocity vector. So the change in our velocity is opposite the velocity direction, so that means we're slowing down, right? Anytime your acceleration and velocity are pointing in different directions, that means you're slowing down. Okay, and then at time equals 5 seconds, we have negative velocity of negative 25 meters per second, and we have negative acceleration. So we have negative velocity and negative acceleration. Both of our velocity and our acceleration vectors are pointing in the negative x direction. Since acceleration is pointing in the same direction as our velocity, that means we're speeding up, right? Our velocity is getting more and more negative with time. So now we're speeding up. Okay, so we went from slowing down to speeding up. So in between, what happened? Well, we actually turned around. And if you actually plug in into this chart, if we actually solve time equals 4 seconds, we could find that at that moment we have velocity of 20 times 4 minus 5 times 4 squared, or 20 minus 20, or 0 meters per second. So at time equals 4 seconds, we turned around. So we went from slowing down at time equals 3 seconds to stopped momentarily at time equals 4 seconds to speeding up in the minus x direction at time equals 5 seconds. So that's our kind of interpretation of what's going on here. And I encourage you to graph these, and that will also help you to understand. Okay.